lesson is on the universal law of gravitation. The reason that the universal law of gravitation is being taught here is because when we first looked at examples of centripetal force, one of the examples was that of orbit. Here I have the moon going around the Earth, and we said what provides that inward centripetal force? Well, it's the force due to gravity. Earth is exerting a gravitational force on the moon, and the moon is exerting an equal and opposite gravitational force on the Earth. But the question is, how much gravitational force does the moon feel from the Earth? And gravitational force, up until this point, we've been using the equation that the force due to gravity, or in other words, the weight, is equal to m times g, where g is 9.8 meters per second squared. But where the moon is located, which is quite far from the surface of the Earth, we cannot use g as 9.8 meters per second squared because this is the gravitational field strength at the surface of the Earth. The moon is not on the surface of the Earth. So we have to come up with a different equation to figure out how much gravitational force there is between the moon and the Earth. And then what we can do is, once we've learned that, we can say, well, then that force is going to be the centripetal force on the moon, keeping it in orbit. Let's look at a simulation and see if it can help us figure out how to calculate the amount of gravitational force between two objects. Simulation comes from physicsclassroom.com. What I have two objects. In this case, it's a planet and a moon, and they are exerting a gravitational force on one another. And as you increase or decrease certain variables, you'll notice that the force changes. For example, if I were to take and move the moon farther from the Earth or from the planet, you'll notice that that gravitational force is getting smaller. As if I move them closer, it's getting larger. So the distance between the moon and the planet is definitely contributing to how much force that the two are feeling. The other thing that's going to affect the amount of force between the two are the masses. If I increase the mass of the moon, notice the amount of force increasing. If I increase the mass of the planet, notice the amount of force increasing. Also notice that I can't increase one without increasing the other, which is Newton's third law. So the factors that affect the amount of gravitational force between two objects are going to be, one, the distance between those two objects, which we're going to use the variable r, the mass of one object, and the mass of the second object, so m1 and m2. Seeing that increasing the mass increases the gravitational force and increasing the distance decreases the gravitational force, then this is the equation that we are left with. The gravitational force between two objects would be equal to g, which is some sort of constant. It's the universal law of gravitational constant, and that's going to equal 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. I'll explain what that means in a moment. But anyway, the equation for gravitational force is this constant g times m1 times m2 over r squared. Masses would need to be in kilograms and distance would need to be in meters in order for that gravitational force to be in newtons. Now, being as though a lot of these problems are going to involve the big objects that are far away, what do I use r as? Well, r is going to be the distance from the center of mass of one thing to the center of mass of the other thing. So r is going to be from center of mass to center of mass. Now, what does g mean? What does 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared even mean? Well, what that means is if you have an object that's 1 kilogram and you hold it exactly 1 meter away from another object that is 1 kilogram, we know that these two objects attract one another. Anything with mass attracts to something else with mass. So these are attracting to one another. But with how much force? Well, as you can imagine, it's pretty small. It turns out that in order for these two to be at this distance away, the amount of attraction that they experience is this many newtons. 6.67 times 10 to the negative 11 newtons. So there is a small attractive force when you have 1 kilogram a meter away from another kilogram. It is this amount, and so therefore we use it as a constant in our equation to have any distance and any masses work out to give us the force. Let's try putting this into practice. So we have something called the International Space Station, which goes around the Earth, and at the altitude that it is particularly at above the Earth, it has to go around the Earth every 92 minutes in order for it to stay in orbit. So again, it goes around one time every 92 minutes. So the period being 92 minutes, we want to figure out what that period is in seconds. So if I multiply 92 minutes by 60 seconds for every minute, I end up getting that the period is 5,520 seconds. So that's how long it takes the International Space Station to go around the Earth. The first question asks us to calculate the centripetal force on the space station. And so we know that the space station is moving in a circle. I can figure out the centripetal force by taking mass times the centripetal acceleration, or maybe an easier way to do it for this particular problem would be mass times 4 pi squared r over t squared, which is another way of writing the centripetal acceleration. So I'll do 4 pi squared times the distance between the International Space Station and the center of the Earth, which is going to be 6.8 times 10 to the 6th meters. And then I will divide that by the period, 5,520 seconds squared. And I find that the centripetal force, based on the speed of the space station, is approximately 3.7 times 10 to the 6th newtons. The question says, using that information, calculate the mass of the Earth. Okay, so I'm thinking about the International Space Station, and let's say this is the International Space Station and this is the Earth. As that space station orbits around the Earth, there's going to be a centripetal force acting on the space station, which is due to the gravitational force. So the sum of the forces in the radial direction on the space station is the centripetal force, which in this situation is going to be the gravitational force. And the gravitational force we just learned was G times m1, which we'll say is the mass of the space station, times m2, the mass of the Earth, divided by the distance between them squared. I already figured out what the centripetal force was, and so what I'm going to do is I'm going to rearrange the equation to get the mass of the Earth by itself. So I take that centripetal force that I found earlier times the distance squared between the space station and the center of the Earth, divided by the constant 6.67 times 10 to the negative 11th, and the mass of the satellite, which is 4.2 times 10 to the 5th. And I end up getting that the mass of the Earth is approximately, with a little bit of rounding here, it's going to approximately be 6 times 10 to the 24th kilograms, which we can look up the mass of the Earth, and it is approximately that. I think they say typically 5.98 times 10 to the 24th kilograms. The final question says, calculate the force that the space station exerts on the Earth. Well, if we already learned that the Earth exerts this much force on the space station, then the amount of force that the space station exerts on the Earth would be the same. That's according to Newton's third law. Something to notice about the law of gravitation, which is that the gravitational force is equal to G times m1 times m2 over r squared, is that it is an inverse squared relationship. Or in other words, we know that G is a constant, and if I'm not changing either object, if I'm keeping m1 and m2 the same, then we could say that the gravitational force is proportional to 1 over r squared, which means, again, if I keep those objects the same, but I move them, I can very easily then predict the resulting gravitational force. Let's see what I mean by this. Suppose I have some object that on the surface of the Earth, the amount of gravitational force between the object and the Earth is 270 newtons. Again, that's going to be when it's on the surface of the Earth. The object is 1 Earth's radius from the center of the Earth. if I were to move this so that it's now 2 times the Earth's radius above the surface, so something way up here, so that between where it was and where it's ended is not 1 Earth radius, but 2 Earth radius above, the question is how much force would it feel at that location? Let's start by looking at it at 1 Earth's radius above the surface of the Earth. So what I've done is I've doubled the distance from the center of the Earth. We were 1, now we are 2. And so since the gravitational force is proportional to 1 over r squared, and I now am going to double the radius, I now will experience a quarter of that gravitational force. So the amount of force we're going to feel here is a quarter of that 270 newtons. Whereas if I moved this object there, I've now tripled the initial from where I was initially. And so if I do 1 over 3 squared, I'm going to get 1/9 of the gravitational force. Or in other words, at this location, the object is going to feel 1/9 of that 270 newtons. And so to answer the question, 30 newtons of gravitational force will be experienced when the object is that far from the Earth. So there's just one more thing I want to take a look at, and that is figuring out what the acceleration due to gravity or the gravitational field strength of the Earth is at locations other than at the surface. And we can use the idea of the force due to gravity, the equation that we just learned, to figure out what little g is at various locations. So let's start with at the surface. We know that g is 9.8 meters per second squared at the surface of the Earth. But what I'm going to do is I'm going to derive that by putting an object right on the surface of the Earth. We have 2 equations to find the gravitational force between the object and the Earth. One of the equations is mg, or in other words, take the mass of the object times the g of the Earth. The other equation that we know is capital G times m1 times m2 over r squared, where in this situation, r, the distance between the center of the Earth and the object, is essentially the radius of the Earth. So I can set these two equal to one another, and I get mass of object, g of Earth, equals g times mass of object times mass of Earth divided by the radius of Earth squared. And we see how the mass of the object cancels. And g, the acceleration due to gravity on the surface of the Earth, is going to be capital G times the mass of the Earth divided by the radius of the Earth squared. If I plugged in the information for the mass of the Earth and the radius of the Earth, I would get g is 9.8 meters per second squared. But then what if I moved this object so that it was some distance above the Earth? How could I calculate g, like 100 kilometers above Earth's surface? Well, the g at that location from the Earth will be g, capital G, times the mass of the Earth divided by, well, we'll take the radius of the Earth plus 100 kilometers, or 100,000 meters, and square that number. That will tell me then the g from the Earth at the location 100 kilometers above Earth's surface. Let's try a practice problem. Given the mass and the radius of Jupiter, predict the acceleration due to gravity, and I'm looking for it on the surface of Jupiter. And then what would be the weight of a 68 kilogram person be at that location? So we know that to find the g for a particular planet, in this case Jupiter, I'm going to take capital G times the mass of Jupiter divided by the radius of Jupiter squared, and that's going to tell me what the acceleration due to gravity is on the surface of Jupiter. Plugging in these values for the acceleration due to gravity on the surface of Jupiter gives me 26.1 meters per second squared. And so the second follow-up question asks, what would be the weight of a 68 kilogram person who's placed on the surface of Jupiter? Well, I could, to find the force due to gravity, I could take the mass of that person times the acceleration due to gravity of Jupiter, which I just found, and do 68 kilograms times 26.1 meters per second squared, and I would find that that weight or gravitational force would be 1,774 newtons. That'd be one way to do it. The other way I could do this is I could just simply use the equation that we learned today, where I'm going to take capital G times the mass of the person times the mass of Jupiter divided by the distance between them, which would just simply be the radius of Jupiter squared, and I'd get that same answer.